Hello, welcome to the lecture series of Discrete Fourier Transform and Fast Fourier Transform. Today we are going to cover the properties of Discrete Fourier Transform, which is the sequence of DFT part 2. In part 1 we have discussed introduction of DFT, from where it was derived, and today we are going to cover these properties of DFT. See, why we use properties? Properties is the key techniques by which we can reduce the computation step and we make our algorithm fast, and some of the techniques gives us that avoiding all the tedious pre-processing of any kind of signal processing in digital domain. So let us see what is the properties of DFT. The properties of DFT, we have number of properties, like we have already seen in LTI system, in Z transform, Laplace transform, any kind of transform. The properties are very similar. So here in the DFT we have periodicity, linearity, circular symmetry, circular convolution, time reversal of a sequence, correlation property, and Parseval theorems. Some more properties are there which includes within the circular symmetry and within the circular convolution and within the correlation. So we'll take step by step when this topic comes. Today we are going to cover this periodicity, linearity, circular symmetry, and circular convolution. The properties of DFT and definition of DFT. We know that DFT says xk, the Fourier transform of a periodic sequence, is periodic if xn is periodic. Xk is periodic if xn is periodic. This is periodicity. Now, but the definition of DFT also says that we start with the DTFT, also we start with the periodic sequence. But what happens if we don't have periodic sequence and we'll have to take the transform and to make this computation periodic? So these are the questions. DFT, xk, you can have let's 1, and IDFT, question 2. Now the target is, in place of sampling, 2 pi interval of this sampling is broken into n samples. If we carry out computation in the way that this n is equal to n plus n, it's the n samples, and 2 pi interval is broken into n sample. So what we do, in place of this n, we substitute this n plus n. So what happens, there is in the equation we can see that there will be no change in the xk if we have n plus n. And similarly we change in this second equation. When we assume that xn is not periodic, that time suppose we replace here that this n plus n again, then we see that there is also no change in the xn. But this part says that changing in this n plus n forced to xn to be periodic, even it was not. I noted down. If we change this sample, then in equation 1 no change, it means no change in xk and in equation 2, no change but forced to be periodic. Now the property states that if xn plus n, there is no change for all values of n, and xk plus n will be the xk for all values of k. Also, the noticeable point is that when sampling period we are taking this n plus n, so what should be the limit? The limit we know by the definition that should be 0 to n minus 1. Why so? Because if we are taking this signal from 0 to n minus 1 samples, then there will be no overlapping. And if we take again n plus n, so we see that there is no change in the xk. So if no change in the xk shows that e to the power j omega, no overlap is there. Why I am talking about the overlap? Just because we are making it periodic. When n is equal to n plus n, it means the repetition of the x e to the power j omega is there for n samples. So it should repeat for repeat after n samples. Now after n samples it will repeat, then whatever the finite sequence we had, it will repeat after n samples, and then there will be no overlap if we have the finite sequence and we are taking n plus n, so x e j omega, no overlap. But if we cross the limit of this, if we have beyond the limit of n minus 1, but beyond the limit of n minus 1 samples, overlapping is there. And because of this overlapping, aliasing problem creates. Along with the sampling, it is the requirement of DFT that it should be periodic, and periodic with the limit of 0 to n minus 1. Then periodicity property says that if we are carrying out this n plus n period samples and continuously the signal is in computation, and we are and that time if no overlapping is there, then no aliasing problem. If overlapping is there after n samples, it will create a problem. So this is the periodicity equation. This is the xn plus n xn and xk plus n xk for all values of k. So we conclude this property that for making the periodicity of xn, it is necessary to take the within the limit of 0 to n minus 1 n plus n samples, where we are broken up the 2 pi samples interval into n samples, and this is the limit. After that, overlapping of x k will be there, which creates aliasing problem. So Fourier transform should be strictly executed for n minus 1 samples. you can have its proof. You can this is very easy property, and no need to have this proof, but still if you want to discuss about this proof, then I just brief it. For proof you do by yourself, I just give you the value. Then in xk, what we are going to do, we have this value, and what we do, okay, and shift this transformed value, shift k by k plus n. Okay, so that would be k plus n. In this we are shifting this, so the equation become n minus 1 with xn, and we'll be having e to the power minus j 2 pi, and we substitute this k plus n and n. Okay. Now you can solve it very easily. We have two values, so it will become in terms of e to the power minus j 2 pi k and e to the power minus j 2 pi n. So while you are computing it, I can just give the hint that we know that 2 pi n is equal to cos 2 pi n minus j 2 pi n for an integer. So when you will solve it, then you will find this condition, and you know what is the value of cos 2 pi n? It is 1. And what is the value of sine? J sine 2 pi n. This will be the value. So cos 2 pi n is 1 and j sine 2 pi n will be 0. So when we are solving this very simply, then substituting this value in this equation, and we get the two terms of this e. So finally we get this x of k plus n will be xk, because this term will be removed and only this xk equation will be there. So it is very easy to prove it. You can do it by yourself. Only this point will be noticeable. Now the second property we have, the linearity. It's very important property. I think so many times in the subject of DSP we have studied this linearity. Linearity which satisfies superposition principle. Superposition principle, what? Then we have two arbitrary constants A1, A and B. Then if two sequences are there, so we are dealing with the DFT, so we'll take two finite sequence. So let we have two finite sequence x1n and x2n. When they are linearly combined, then in such a way that A x1n plus B x2n is the sequences, then its DFT, endpoint DFT will be xk A x1n plus B x2n. It's very simple. For the value of n, which is max limit for samples n1, n2. So where n1 is less than n2, then x1k and x2k will have the limit of k 0, 1 to n2 minus 1. This is the limit of linearly combined sequence. So we can substitute this value into the transform equation. This value just substitute in the xn in transform equation. Here we substitute here this value, and then we'll have a separate value that you can prove. You can have this proof also, but I'm not going to solve it completely. That is one. We'll be having a x1 n e to the power minus j 2 pi n k by n, and plus again it would be summation of x2n e to the power minus j 2 pi n k over n. Now a and b are the arbitrary constants, so a and b are constant, so we can take it out from summation, so that xk take out of summation. So xk will be definitely a x1n plus b x2n. This is the linearity property. Very simple. The symmetry property. Symmetry property is very important property we have. See, all those property we have seen in all the transforms except these two. This is the most significant property of DFT, circular symmetry and circular convolution. These two properties are not in Z. These two properties are not in Z. So it is very important. And we can say that this is the feature of DFT, in fact. So we'll see the circular symmetry, and before that I think Fourier transform, continuous Fourier transform already concluded about some properties, some relations of symmetry. I have just listed out here, then we'll do as a requirement of using these all, then we'll see later on what will be the details of it. But I just listed out it here that xn is DFT x e j omega, then the folder sequence x of minus n will be x e to the power j omega e to the power minus j omega. If xn is complex, then the real part xn is 1 by 2, that is cos function. We take cos plus j sin theta. So cos function 1 by 2 x e to the power j omega plus x complex conjugate of e to the power minus j omega. If xn is complex, then imaginary part of this xn is 1 over 2j x e j omega minus x complex conjugate of e to the power minus j omega. And these are the complex values relations. With symmetry relations, we know that xn is having x e to the power j omega Fourier transform, then it consists of two parts, x real and imaginary. Real is even xn and imaginary is odd xn. So we'll approach in this way. Also in introduction I told you about that whenever we are going through the computation, we take imaginary part multiplication with j and will be treated within the real part. So we compute with real calculations. If we have complex conjugate, then that is x e j omega is x complex conjugate of e to the power minus j omega. So the real part of this x e j omega will be real part of x e to the power minus j omega. And this omega we take plus or minus. The omega changes negative does not make any difference in the sampling, because we are taking the angular omega. So it does not make any change if we take omega in positive or negative. So x e to the power j omega is if repetition in angle omega is there, then we can have this imaginary part, that is minus x e to the power j omega. Just for review, I listed out these properties, and we can see that the symmetry property is absolutely depending on the shifting of the sequences. So shifting property is there, that how we do the shifting for making the symmetry, and why the symmetry is circular, we'll see later on. So that xn is, we have, suppose we are shifting n minus ln. So take this, L is minus infinity to infinity, and x n minus ln for the length L which is less than capital N. Then this x n minus k shifting will be x n minus k minus ln. And if xn we take finite length, then this sequence varies from 0 to n minus 1 and no overlap. So it can be shifted. If overlapping is there, we can't shift in circular. So this equation now says that if xn is in finite length, we are shifting in this manner, then this shifting will be producing no overlap, and we can call it circular shifting. So this shifting, I can write it like, suppose this x dash n is the shifting value, then n minus k for n lying from n minus 1 and 0 otherwise. So this equation is circular shift. It means, what is circular shift? It means repeat after n sample, n point repeating, and periodic. Now it is periodic. So circular shift can be represented, this circular shift can be represented in index modulo n, and I can write it like x dash n is x n minus k modulo n. Values should be n minus 1 to avoid the overlapping, and shifting till n point, then after n point it is repeating. It means after n point the first point will be repeated there, and every time this called index modulo. So it can be represented in terms of index modulo. It sometimes it is also written as n minus k and n. So this is modulo n. Now before studying this circular symmetry or the calculation, let us learn about how mod n, index modulo n, is being calculated. So that is very important. The circular shift and calculation of index modulo. n. Suppose we take this sample 0, 1, 2, 3, then 4, 5, 6, 7. This is n. Minus 1, minus 2, minus 3, minus 4. So this is the finite length sequence. We have, let it be xn. No need of amplitude. I am just giving the example how we make it periodic. So now when this is shifted and we are making it periodic. How we make it periodic? I have we have discussed it, periodicity problem, and taking this kind of shifting and with the limit n minus 1 samples. So after n point it will be repeating. So as it will be repeating, then I just draw the x dash n. X dash n means the periodic sequence. So I just draw it periodic sequence. 0, 1, 2, 3, then again 4, 5, 6 and 7. Then again at 8 and so on. Similarly in the negative side, minus 1, minus 2, minus 3, minus 4. So this is x dash n. Now we'll take the fast, and our target is to calculate x is equal to x n minus k mod n. So I just give one example. We take k equal to 2 and n equal to 4 in this section, and how we calculate it, see, carefully listen. For n equal to 0, we have taken this condition. So x dash n will be x index modulo of 0 minus 2, 4. That will be x 4 will equal to x2. How we do it? What exactly? I mean, there are so many methods. Different authors explains with different. The modulo n can be added to n and then n, take n1 plus n2 something. What I, in the shortcut I do, I just add it these two. Listen carefully. I just add it these two, and then whatever the value will take the sequence from this. We have made it periodic. So this is 4 minus 2, x of minus 2. 4. So it would be x2. When n equal to 0, this value is minus 2. So our 4 minus 2, it will be x2. x2, whatever the amplitude of x2 will be shifted here at origin. So this periodic will be shifted to the x. At n equal to 1, this is 0, then take 1, x, 1 minus 2, 4. So it will be x of minus 1, 4. That will be x3. Similarly, x2 is x2. Then we'll be having x0 and x. Many books will directly reckon x0. So I just write here that it would be 4. X0. What is at 4? The value of 0. This is 4. At 4, the 0 value is repeating. So x4, the 0 value is repeating. Similarly, n equal to 3, we'll have to do for n equal to 4. So x dash 3 will be n minus k, means 3 minus 2. So we'll have x1, 4. Actually, we go for it x5. But at 5 we have the value of x1. So I write it x1. This is the circular shift and modulo and calculation. This will be modulo and calculation. So this circular shift calculation give the computation. If we know how to calculate this modulo n, then it would be easy to understand the circular shift. This is, and in Oppenheim-Scheffer, the very nice example is given that if suppose this shifting is on the circumference of a cylinder, just imagine, so the last sequence will come to the origin value. So when this sequence will go again, repeating again and again, then we'll see that this finite sequence will go there and then again, then it will come to the minus values and will come to the original value. So we see that this is in the nature circular. So we call it circular shifting, and this is with the, this can be represented in modulo n. Okay, now we'll see the circular shift property is used in circular convolution. So our next property is circular convolution, which can be represented by using this circular shifting and calculation by modulo n.